You know, in the world of chemistry, you've got your supporting actors, and then you have the true stars of the show. Today, we are talking about a real headliner, the carboxylic acid. This molecule is just so versatile, it's the creative force behind so many other compounds. Truly, a master building block. All right, so here's how we're going to break it down. First, we'll look at its structure, which gives it this kind of split personality. Then we'll get into its most famous feature, its acidity. After that, we'll see its amazing talent for transformation, meet its whole reactive family of derivatives, and then we'll wrap it all up by seeing why it's really earned the title of chemistry's master building block. Okay, first things first, let's really get to the heart of what a carboxylic acid is. Because honestly, everything it does, from how it behaves to how it reacts, it all boils down to the super clever way this molecule is put together. And here it is, the source of that split personality. You've got a carbonyl group, right? Just like you'd find in a ketone. And you've got a hydroxyl group, like in an alcohol. Well, when you fuse them together on the very same carbon atom, bam, you get something completely new and unique, the carboxyl group. It's a functional group with a character all its own. Now, this special structure makes these molecules incredibly, well, social. That carboxyl group is so polarized that it lets them form these super strong connections with each other, called hydrogen bonds. And that is the secret behind their surprisingly high boiling points. We're talking much higher than even alcohols of a similar size. And just how social are they? Well, under the right conditions, they don't just hang out. They literally pair up for life in what we call a dimer. Two molecules will lock together so perfectly with hydrogen bonds that they start acting like one giant molecule. This little detail actually stumped chemists for a while until they finally figured out this unique pairing. So that structure makes it social, sure, but it also gives the carboxylic acid its most famous trait, the one that's right there in the name, its acidity. We've all tasted it in vinegar, but what's the deal? What actually makes it so much more acidic than its chemical cousin, the alcohol? Okay, so the strength of any acid really just boils down to one simple thing. How stable is the partner? That's the negative ion or conjugate base that gets left behind after the acid gives away its proton. See, a more stable partner means the original acid was stronger because the whole system is just way more comfortable in that state. And here's that power play in action. When an alcohol loses its proton, you get an alkoxide ion, and that whole negative charge is stuck, localized on just one oxygen atom. But look at the carboxylate ion. When the carboxylic acid gives up its proton, that negative charge gets to be shared. It's delocalized across two super greedy oxygen atoms. That sharing, which we call resonance, makes the carboxylate ion unbelievably stable, and that is the secret to its strength. And, well, the numbers really speak for themselves. Just remember, a lower pKa means a stronger acid. So ethanol, a typical alcohol, is way up there with a pKa of 16. Phenol does better, around 10. But ethanoic acid, yeah, the stuff in vinegar, is all the way down around 4.8. And because pKa is a logarithmic scale, that's not just a little more acidic, it's thousands of times more acidic than phenol, and literally trillions of times more acidic than ethanol. It's not even in the same league. All right, so we know what this molecule is like. Now let's talk about what it does. Carboxylic acids have this incredible talent for transformation, which is exactly why there's such a massive deal in synthetic chemistry. Now for one of its signature moves. While other molecules like alcohols and phenols aren't really acidic enough to react with a weak base, a carboxylic acid definitely is. Mix it with something simple like sodium carbonate, and what happens? Bubbles. That fizzing, that effervescence, is the release of carbon dioxide gas, and it's a simple, unmistakable visual test that just screams, hey, you've got a carboxylic acid here. But maybe its most famous transformation of all is making esters. This is where chemistry gets delicious. You react a carboxylic acid with an alcohol, add a little acid catalyst, and you create these amazing molecules that are responsible for so many of the world's best smells and flavors. I'm talking pineapples, bananas, pears, even the scent of many flowers comes from esters. But the transformations aren't all fruity and sweet. They can get a lot more, well, intense. By reacting a carboxylic acid with something like phosphorus pentachloride, you can swap out that entire hydroxyl group for just a single chlorine atom. This creates an acyl chloride, which is kind of like a supercharged, aggressive version of the original acid. It is incredibly reactive, and it's a critical stepping stone for making a huge variety of other compounds. And that super reactive acyl chloride It leads us perfectly to the rest of the family, the carboxylic acid derivatives. You can think of these as all the different molecules that you can make from, or even turn back into, a carboxylic acid. Now, this family has a very clear pecking order, a hierarchy of reactivity. Way up at the top, you've got the acyl chloride. We'll call it the hothead of the family, just ready to react with anything. Then you have the acid itself, the patriarch. Then the more stable ester, and finally, at the very bottom, you have the very stable, pretty unreactive amide. So what makes the acyl chloride such a hothead? Well, it's pretty much a perfect storm of reactivity. First, its central carbon atom is basically a giant target just begging to be attacked by other molecules. Second, that chloride ion is what we call an excellent leaving group. It's more than happy to just pop off the molecule. And third, the bond holding it there is pretty weak and easy to break. It's practically designed to react. And knowing this reactivity ladder is super useful. Take breaking down esters, for instance, in a process called hydrolysis. If you use an acid, you get a slow reaction that can actually go backwards. But if you switch to a base, the whole game changes. The reaction is fast, and here's the kicker. It's a one-way street. It's irreversible. That's because the base immediately grabs the carboxylic acid product the moment it's made, which just drives the reaction forward until every last bit of the ester is gone. So let's put it all together, right? You've got this totally unique structure, you've got this powerful acidity that you can fine-tune, and you've got this incredible talent for transformation. What do you end up with? You end up with one of the most vital, most versatile building blocks in all of organic chemistry. And it really is like a central hub on the map of organic chemistry. It's a total two-way street. You have countless different reaction pathways that all lead to making carboxylic acids. And then, from that one point, a whole new universe of paths branch out to create that entire family of derivatives and so much more. It's like the grand central station of molecules. This quote really gets to the heart of what makes this molecule so special. See, most compounds with a carbon-oxygen double bond, these so-called unsaturated compounds, they like to add things. They break their double bond to make room for new atoms. But carboxylic acids? Nah, they play a different game. Because they have a piece that's willing to leave, that hydroxyl group, they prefer to substitute. They swap parts out. And that seemingly small difference in behavior is what unlocks a completely different world of chemical possibilities. It's what makes them so incredibly versatile. And that incredible versatility is exactly why carboxylic acids and their derivatives are literally everywhere, from the food we eat and the medicines that keep us healthy to the plastics and polymers that build our modern world. They really are a master building block, which leaves us with one final, very exciting question. What on earth will chemistry build with them next?